Let's see how we can. That's good. Okay. All right. Got a lot of ground to cover. Bonding is a pretty big subject. That's why it takes 2 chapters. And for quite some time, the topic of bonding among research scientists was they sort of skirted the issues. It wasn't until Linus Pauling got hold of all the information and brought it together into a coherent expression that, and actually he wrote, I think it was a book, or at least a research article, The Nature of the Chemical Bond. And he got a Nobel Prize for it too. So that's nice. So what do we mean by a chemical bond? We just throw that term around like we know what it means, right? Well, we're going to look at that, what do we mean by chemical bond? And actually, these questions assume that we've defined the chemical bond. The chemical bond is simply an expression of an association, if you will, between 2 atoms. And to anthropomorphize, they want to be there. They want to be connected to one another. We're going to look at why that happens. Yes and no. There really is no simple explanation for the chemical bond. But we have learned quite a bit about what draws atoms together. And one way to look at it is what's the total energy of all the atoms that would come together in a compound. And if you look at the energies of the atoms, or if you're breaking bonds to form others in a chemical reaction, say you have 2 compounds come together and they rearrange atoms and make different compounds. The overarching argument for that reaction to proceed is that the energy of the products is lower than the energy of the reactants. It's a downhill ride. If you can get your energy level up here and you can get it down here, it wants to be lower. Now that also can be tricky, because then you wonder, well, how do we store so much energy in compounds? Sometimes we can spontaneously produce explosives, and they've got more energy than the reactants, right? Well, it's a local phenomenon. When you put sulfuric acid, nitric acid together with glycerol, you get nitroglycerin, which has more energy than the reactants. But the local, it's in a local dip here. So we put those reactants together, and under temperature, high temperature, you get them over this hump, and then you stick them right in there. So technically, at this point they got high energy, at this point they got low energy. So temporarily, that compound is in here, although it's very unstable. In other words, all you have to do is just like that, kicks it over this one, and away she goes. And you're, well, depending on how close you are when it goes off, you could be in deep trouble. Okay, so the simplest example of the formation of a chemical bond is 2 hydrogen atoms approaching to form H2. So this is to represent the electron cloud And it also emphasizes the fact that when two atoms approach, they may form a bond, they may not, but as they approach, the first thing they see is their electron cloud. So that's where the bonds form. So we get this intermingling of electron densities, and eventually we find ourselves with two hydrogen atoms and a concentration of electron density between the atoms. It tends to be higher in this region that we would call the bond than it is in any other region, but the probability is still there that the electrons could spend some time out here, right? So each one of these is not an electron. It's an indicator of where you might find an electron at any one time. So the probability tends to be greatest in between them, and that signifies a bond. Another way to look at it is, actually the best way to look at this graph is to start out here and work backwards, because this is the distance between the nuclei of the two hydrogen atoms. So they're getting closer as you move this direction. That makes more sense to form a bond. So they're far apart here, and their potential energy relative to one another is 0. But as they get closer, we find that their potential energy drops. And of course, as the energy drops, that's a preferred state. And you end up down here with an ideal distance and the bond length. But if we try to push them together closer, what's happening? Well, you're trying to push those two protons together now, and they resist. Right? So there's an ideal distance also for bonds. What types of bonds are there? Well, in simplest terms, you could either have an ionic bond or a covalent bond. An ionic bond is a bond that forms between two charged atoms, a positive one and a negative one. And in that case, one way of looking at it is, as the neutral atoms approach one another, the electronegativity, well, we haven't defined that yet, but the strength of attraction of electrons by one atom is greater than it is for the other one, to the extent that one of them steals one or more electrons from the other one. And that being the case, you produce an excess negative charge on one and a deficiency of negative on the other one, which makes it positive. Then the bond is strictly electrostatic. However, if the two atoms competing for electrons are similar in their strength of attraction for electrons, then those electrons will spend time around one and spend time around another one. And in that case, they actually share the electrons. And that's what we mean by a covalent bond. Now, strictly this is not true. Electrons are shared equally by the nuclei. It is if they are identical. Right? You have two nitrogens bonding together. Actually, there are three, but I'll explain that in a minute. Then the electrons will spend the same amount of time around each one. But if they're not equal, right, if they're like this, I think that's right, 2, 4, 6, 8, 2, 4, 6, 8, 4, 4. Then they're going to spend more time around the oxygen than they do around the carbon. So it's still a sharing of electrons, but it's not an equal sharing. So that's not strictly true. So we have to say, well, what happens if they're still sharing, but some electron time is spent more around one than the other? Well, then you start to get into a condition called polarity. So you have an unequal distribution, which gives you a slightly negative charge around one and a slightly positive around the other. And then you have a polar covalent bond. So if they're shared equally or almost equally, we say they're a nonpolar covalent bond. Hydrogen fluoride is a good example. And we can actually measure how polar that bond is by placing it between two charged plates and measuring its the ability of that compound to transfer the charge. If it's very polar, then you get a large transfer of charge from one plate to the other. And if it's virtually non-polar, then you don't get any charge transfer. And it's measurable. So in that case, now let's reiterate. The chemical bond then is an expression of the forces that hold atoms together. And consequently, they function as a unit. Okay. So if you have an ionic bond, then you really have a collection of positives and negatives, like sodium chloride, say. Right? You have your sodium surrounded by negatives, but your negatives are also surrounded by positives. Right? So you get a crystal structure. And the expression of sodium chloride like that is simply the smallest whole number ratio of one ion for the other. They don't function as individual units. That's typical of ionic compounds. But for covalently bonded compounds, which are often referred to as molecular compounds, they do function as separate entities, like water or carbon dioxide, or the diatomic elements. They're molecular. They behave independently of one another. And these will be covalently bonded atoms in that molecule. So this is as good as explanation of why as any. If the energy level drops in the process of forming the bond, then that's an explanation for why it formed in the first place. Because things tend toward the lowest energy state that they can get under those local conditions. So they either share electrons or they completely transfer electrons. That's the short answer. So now a discussion of electronegativity. Electronegativity is an expression of how strongly an atom draws electrons to itself. So high electronegative atom will have a very strong pull on electrons. Low electronegativity means they prefer to give them up. For lack of a better explanation. But they can be quantified. That these values can be quantified, and there are several systems, but the most commonly used is the Pauling method of determining electronegativity. And that's the same Pauling, Linus Pauling, that got the Nobel. You don't have to know this calculation. Just know how to use the numbers. Right? Let's see. Okay. So we're going to go back to the periodic table and see if we detect trends in the electronegativity of atoms. And in fact, we do. So if you're in a group, you find that the electronegativity increases from bottom to top. And the reason for that is that the bottom elements have more electrons surrounding the core or the nucleus, and they tend to shield that positive charge from any approaching electrons from the outside. So, and the term we use is effective nuclear charge. So the effective nuclear charge of the elements in the bottom of a group is actually lower than the effective nuclear charge of those toward the top. So the converse of that is from bottom to top, you increase the electronegativity of the atom. From left to right, you're not adding electrons to a larger energy shell as you would be in a group. So as you add protons from left to right, you're actually increasing the effective nuclear charge. So from left to right, you increase the electronegativity. From bottom to top, you increase the electronegativity. So put those two trends together, lower left to upper right, you're increasing electronegativity. And in fact, the most electronegative atom is fluorine. Some authors report 3.9 or 3.95, but it's easier for me to remember 4. I just say it's 4. And then the lowest electronegative is francium in the lower left-hand corner. Here's another way to look at it. The electronegativity is rendered as the size of the cube or the pillar, right? So this one's going to be really big. This one's going to be really small. And the trend is generally left to right, even through the transition metals, except for right here. So you get over here, and then the electronegativity goes down right here. Got any ideas? What is it about that last group in the transition metals? Filling which orbital? The D, right? Filling the D orbital, and at this point, the D orbital is full. So that lends a little stability to the atom, and it really would just rather not have any extra electrons. So that's why it drops here. But then it takes off again here as you get into the p orbitals and increases again. Okay. So from lithium to fluorine, lithium's on the far left, fluorine's on the far right in the same period. So the fluorine would have the more attraction for electrons. So if we form a bond between fluorine, well, let's see, in a bond between fluorine and iodine, which may sound crazy, but it does happen. Between fluorine and iodine, which has more attraction for electron? Well, iodine's down here, fluorine's up here, so fluorine has a stronger attraction. And fluorine, again, would have a stronger attraction for the electrons. Now that bond is going to be covalent, but still, the stronger attraction is to fluorine. We've already done that. Okay. Now there are values associated. If you want to know whether the bond is non-polar covalent, polar covalent, or ionic, there's not a lot of controversy, but some as to where you place the position. If you look at the electronegativity of each of the atoms in the bond, subtract the smaller from the larger and see what the difference is, then the ionic, I think, would be 2 or greater in that neighborhood. And the breaking line for polar to covalent to nonpolar is in the neighborhood of, let's see, maybe 1.5. Do I have a slide on that? I hope I put a slide on that. Yeah. Oh well. That's what I get for trying to work from memory. But there, another point to be made from this slide is that if you're on a continuum, right, and we can call it polar covalent, but the real value of the polarity of that bond rests in the difference in electronegativity between the two atoms. Let's see if we can put these in order. Arrange the following in most to least polar. So the most polar will be, of course, the one with the greatest difference, right? And for this one, we've got fluorine compared to the rest of them. So all we have to do is say, what's the relationship between carbon, oxygen, and nitrogen on the table? So there's carbon over here, nitrogen there, oxygen there. Oxygen's closest to fluorine, so it'll be the least. So it should go from most to least would be carbon, nitrogen, oxygen. Carbon, nitrogen, oxygen bonding. So this is the least polar, this is the most polar, simply because they're the farthest apart from fluorine. This one's a little trickier. We're comparing carbon and fluorine, which is in the same period, and it's 3 steps away from each other. Nitrogen and oxygen, they're right next to each other. And silicon and fluorine are probably the farthest apart, so they should be the greatest. Nitrogen and oxygen should be the least. So most least. So this one, then this one, then that one. Oops. Okay, where's the answer? Okay, the last one, the least is going to be the one where you have the same atoms bonded with each other. And then the greatest is, we just see the difference between boron and sulfur. So boron is there, sulfur is here. So sulfur is really closer to chlorine than boron is. So boron chlorine should be the most polar. Come on. And the least polar will be dichlorine. Okay. All right, test taking technique. Which of the following bonds would be the least polar, yet still be considered polar? Well, of course, magnesium oxide is ionic, so you throw that one out right away. And oxygen can't be polar because they're equally pulling. So all we have to do is put carbon, oxygen, silicon, nitrogen in order. So which is the least polar would be the ones that are closest together. So nitrogen and oxygen are the closest together. That makes them the least polar. Well, they're closest together on the periodic table. Let's move on. Okay, terminology. Dipole moment. What do we mean by that? I left the cap off too long. Dipole moment. Well, moment is a physics term, which means vector sum. I mean, it's a vector property. So there's direction involved. So when you have, let's take water. Right. Oxygen is more electronegative than hydrogen. So the trend for attraction is toward oxygen, and we express that with an arrow.
with a little plus sign. So this is the plus side, and this is the way the electrons are pulled. That's what that arrow means. That's a dipole moment for the bond. Okay. For the whole molecule, you do a vector sum, which just means you have to take into account both the magnitude of the force and the direction. And when we add these together as a vector sum, you get that for the entire molecule. So that means this side is going to be slightly negative, this side is slightly positive. That's what that delta means. It means slightly. It's not full. If it's a full charge, we leave the delta off, and it's just a plus. That means there's at least one electron imbalance for that charge. But here, it's only slightly because we only shifted the electron a little bit. Okay. This also illustrates the fact that if you want to know whether a molecule is polar or nonpolar overall, you have to consider two factors. One is polarity of the bonds, and for water we do have polar bonds. And then what's the shape? If water were shaped like this, right, we'd have like that, and the vector sum of that is 0. No polarity for the entire molecule. But the shape tells us that when we sum these dipoles here, we get a net dipole for the whole molecule. So two factors involved: polarity of the bonds and the shape of the molecule. Okay? Let's see, I'm going to have to switch here. Red. Okay, so eventually we're going to have to learn something about the geometry of our molecules too. For the time being, you have to take it on faith that oxygen is bent like that. We'll prove it to you later, and you'll be able to determine those shapes using the techniques that I'll give you in a few minutes. Come on. There we go. Carbon dioxide is a linear molecule like that. They're only showing one bond. That's not exactly true. Carbon dioxide is actually double bonded carbon, but it's linear. So even though the dipole is like that and like that, they cancel out. So carbon dioxide is a nonpolar molecule. Now, I've always wondered about that. Overall, molecule is nonpolar, that's true. But you still get an uneven distribution of electrons out here and out here. So I can't help but believe that that has some effect on the way the molecule behaves. It's not as if we're talking about two nitrogen molecules where you have an even distribution all around. You know, that's definitely nonpolar. While this might be nonpolar, you still get that uneven distribution. So I want to keep that in the back of my head when I consider its properties. Okay. Let's see now. Why is this stuck in here at the moment? Just to illustrate. Okay. So this sulfur and oxygen is slightly polar toward oxygen because oxygen is above sulfur in that group. But the dipole moments are pointing symmetrically away from each other and they cancel out. Similarly, carbon tetrachloride used to be dry cleaning fluid until the EPA and OSHA got hold of it and said you can't use it anymore because it's toxic.
And they were pretty much right. It was making dry cleaning workers sick. But it's very effective at cleaning the oils out of your clothes, right? Because it's nonpolar. So it dissolves, nonpolar dissolves nonpolar, like dissolves like. And then once you wash your clothes in that stuff, and it's very delicate, it's very easy on the fibers. So once you get the oils out of it, and you take that liquid away with the oils, then all you have to do is evaporate the carbon tetrachloride, and the oils are left behind, and then you recondense the CCl4, use it again. But these are all nonpolar molecules simply due to their symmetry. Okay. Now we're going to look at what makes a stable compound. One way to look at it is the atoms in a compound are tending toward noble gas electron configurations. So if you have, say, a nitrogen in a compound, it's there because it is able to claim electron configuration of neon. Right, so it's going to, it's either going to remove 3 electrons from somebody and put them in its p orbital, fill the p orbital up, right? That's 2p. So it's 1s2, 2s2, 2p. Starts off 2p3. So it needs 3 electrons to fill up that orbital. And if it fills up that orbital, then it looks like neon. So we add 3 electrons, we look like, let's see, I'm about to spill over it. We look like neon. Or it can get those electrons by sharing. And when you share electrons as an atom, you're really fooling yourself because you don't really own those electrons, but it feels like you do, right? They only spend part of their time over here, but apparently it's enough to make you think you have a neon configuration. Now, concept of the octet, where does that come from? The octet comes from the concept that you have an S and a P. This could be 3 or 4, doesn't matter. But the S orbital will have 2 electrons, P will have 6 when it's full. Okay? And that's the octet. So, and that works fairly well for elements up here. Actually, the really important elements for biological systems. So the octet concept is extremely useful. Okay. So when you get down into the 4th and higher periods, or principal quantum numbers, then you start to get to a place where the octet breaks down. But the elements are still trying to look like noble gases. It's just they get there, maybe they don't have to get there by octet. It might take 10 or 12 or 14 electrons to get there, but that's where everybody's headed. Okay. So we look at the number of valence electrons, and you just count from the left over. So if we have 1, 2, 3, 4, 5, 6 valence electrons for oxygen, which means we only need 2 more to make 8. So that's one of the reasons for focusing on valence electrons, because those are the ones we have, and then the difference between that and 8 are the ones we want. Okay.
digress for just a moment. What's an isoelectronic series? Isoelectronic. Iso means the same. That's a prefix that means same in Greek. So it has the same electronic configuration. Right? So if this is an isoelectronic series, and we could use neon and compare that with the rest of them. Right? So neon is going to be, what is that, 10? Neon is going to be 1s2 to 2s2 to 6. Okay. Let's see if these others are also. So oxygen, 2 minus, right? Starts with 8, which means it starts with 8, but with the 2 minus charge, we have to add 2 more electrons, makes 10 electrons. Yep, same configuration. Got 10 electrons, they go into position just like neon does. Fluorine starts with 9, and if we make an ion, we got 10 electrons. Okay. You do the same thing with the cations. You just take an electron away from sodium, right? It's got 11. And take one away, you get a positive charge. That means 10 electrons. So these are all the same electronic configuration as neon. They're isoelectronic. Let's see. I'm going the wrong direction. Okay. Have we already done trends? Didn't we do trends already? Or am I thinking of another class? Yeah, we did. Ionization energy, electron affinity. Yeah, we did that already. Okay. So now we've got trends for atomic size. We didn't do ion radius. We did ionization energy, we did electron affinity, and we've done electronegativity. The ion radius follows the same trend as atomic size as long as you have the same charge in the series, in the group or in the period. But if you introduce different charges, then you have to take into consideration, are you adding or subtracting electrons? Generally speaking, if you have a neutral atom and you add an electron, it gets bigger, right? Or if you take away an electron, it shrinks. That's why the natural ion for sodium is much smaller than the neutral atom. Okay, if we look at binary ionic compounds, that is, we have one cation and one anion. Well, actually not one. We have a cation and an anion. As long as the charges are balanced, if the charges are equal, of course we have 1 and 1. But if the charges are not equal, then we have to balance the charges with multiples. We can look at the structure of those ionic compounds, similar to the sodium chloride that I sort of sketched out here. They go together in certain ways. Let's just put it that way. And there's a concept that helps us understand how strong the attraction is. It's called the lattice energy. You have to define what the lattice energy is. Go back. Okay. Lattice energy is based on electrostatics.
And here's one of the anions, cation, anion, and there's a proportionality factor, and this is the distance between them. Right? So I see similarities here to Newton's law of universal gravitation. You know, the distance between the bodies influences how strong the pull is, and the size of the bodies. So, and the size of the charge influences how strong the pull is, how much the lattice energy is, and the distance between them also influences that. Okay. So how do we measure that? What do we need to know to measure that lattice energy? Well, remember we were focused on ionization energy and electron affinity in terms of gases that either lose or attract electrons. And we do that because that separates the individual atoms from one another, and then the amount of energy that you get from or you add to is simple. In other words, it's not complicated by other factors like attractions in liquids and solids. That's why we separate them from gases. Well, the lattice energy has a similar concept. What we're doing is we're bringing the gases together to form the solid. So we would have a cation, gas, and an anion, gas, and it forms solid. Okay? And when these two come together, you get energy out. Right? So this is always exothermic. And that's the lattice energy. Let's see. Oh, okay. So now that we have that concept, we look at the steps in forming an ionic solid from the ground state elements. Right? So let's say in this case we've got a metal represented by M and a non-metal represented by X. I'd rather use real, but or we can just do it ourselves. So let's say sodium chloride. Okay. So the first thing that happens, the first step is the metal is going to be a solid. So it has to be converted to a gas. And when you go from a solid to a gas, that's called sublimation, right? And it takes energy. So that's endothermic. So you're putting energy in. So the energy input is positive. Okay. Then you have to ionize it, or you won't get any attraction. Now we're forming ionic solids here. Okay. So we're going to take this gas, and we're going to ionize it. So we form that one as the gas, plus a free electron. Let's see, I was going to do this. I told you I was going to do it, then didn't do it. Sodium. Take that sodium, ionize it. So we have to add energy in there to do that. Okay. Now we have our sodium ion as a gas. Now we have to do a similar thing with the non-metal. And they're saying that our non-metal is diatomic. That's good because chlorine is diatomic. Okay. Chlorine. Yes, that's good. It's a gas at room temperature and pressure. But we only need one of them. So we have to
Oh, we have to convert it. Oh, okay. My mistake. We have to break that bond first. But since we're only going to need one, then we only have the half, and this also is endothermic. Okay. Then we're going to take, the next slide, then we're going to take this gas and we're going to allow it to attract an electron. So we're talking electron affinity. Right? So in that case, we get energy back. So this is exothermic. Okay. Now that we've got the gaseous ion, gaseous anion, and we have the gaseous cation, now we can bring these together. This is the solid. That is extremely exothermic. Okay. So how much energy do we put in or get back from this entire process depends on the summation of each one of these steps. And if you've ever seen sodium solid reacting with chlorine gas, you know that these are almost insignificant. And this one, the overall summation is extremely large exothermic. Oh, there's a representation. Right. So here's the lattice energy. So we're going from the gaseous cation anion to the solid. So this step is the lattice energy right here. And it represents the strength of the bond that forms between these two. It's an estimate of how strong that ionic solid is held together. Okay. Have I described, yeah, when we're doing thermochemistry, I described heats of formation, didn't I? Okay. So you remember that. You always start with the standard temperature and pressure form of the compound, 1 mole of it. And then you work backwards to the elements in their standard states. So lithium is standard as a solid, fluorine is standard as a gas, and in this case, you have to use fractionals usually as coefficients. So there's an enthalpy associated with this formation. So if we break this process down, we take this one first, and we go through these steps. We sublimate the solid to a gas, then we ionize the gas, and then we take the fluorine and we break that bond between the two fluorines by putting energy in. Then we allow it to attract an electron, electron affinity, and then we bring these two together for the lattice energy, and all those together add up to the heat formation. So it's a multi-step process, actually. Okay, let's see. This is just to make a point. There's no such thing as 100% ionic character.
even in compounds that have maximum difference, say fluorine and francium. Right? They are definitely ionic, but there's no such thing as 100% ionic. So the ionic character can be expressed as a percent. We can calculate the dipole for X plus and Y minus, and then measure the dipole moment after they form the bond. So this would be 100% character right here. That's theoretical. And then this is actual dipole of the bond. And that gives you an ionic character. And then we can put them on a chart. The percent ionic character, of course, is very high for lithium and fluorine, right? Cesium fluorine is pretty high. That's strange. Lithium and fluorine have much higher ionic character than cesium and fluorine. So what that tells me is that the electronegativity difference is not the only factor that gives the ionic character. My guess is that since cesium is such a large ion, that its standoff distance from fluorine decreases the strength of the attraction. It's that R, that distance between them. Whereas lithium and fluorine are both small, very small. So that puts that shrinks the bond very close, and that increases the dipole moment of the bond. Okay. This is a practical definition of an ionic compound. First of all, if the compound is ionic and it's solid, that means the ions are locked in place, right? They can't move. So a solid ionic compound is an insulator, an electrical insulator. It will not conduct electricity. So you can take a big cube of rock salt and put 2 electrodes on it, and your light bulb will light. But if you melt it, which takes a lot of heat, if you melt it and use your electrodes, hopefully inert electrodes that can't be corroded, then your light bulb will light, because it will. Now the ions are free to move and conduct the current from one electrode to the other. Same thing happens if you put them in solution. Sodium chloride in solution will conduct electricity, because by putting it in solution, you've separated those ions, so now they can move. That's the key. But that defines an ionic compound. If you melt it, it conducts a current, it's ionic. Okay. I described a model before, haven't I? Whenever you have a theory, it's usually accompanied with a model. In other words, the theory says that the microscopic world should look like this. That's our model. Like a model airplane or a battleship, or build a model. It's not the real battleship. It's just a model of the battleship. But we can use it to see what would happen if we change things. Like if we try to take the 5-inch guns and put them over here, what would that do to the way the ship protects itself? Or if we take the 16-inch guns and maybe take one of them out. It used to have 3, now it's only got 2. So it can't fire as many. So we can change the model and see what effect that has on the overall performance of the model. So similarly, we develop models from theories about how nature actually works, and the model helps inform us about how it behaves if we change certain things. Okay, so the first one I've already described. The model does not equal reality. That's the first important. Models tend to oversimplify, right? Because we can't know every factor that's involved.
in the performance of a theory.
So we oversimplify the model just to make it manageable. Right? That's our first stumbling block. Right? If you make it too simple, then it doesn't adequately describe reality. I mean, it's not an adequate model for reality. That's why models over time generally become more complicated, because we find that our oversimplified model doesn't adequately explain what's happening in the real world. So we tweak it. We add a factor here, add a factor there. It gets more complicated. And there are always assumptions that are made when we produce a model. And if you don't understand these assumptions, or if you ignore them, you do so at your own risk. And that's why many models are misused. For instance, climate models. We have computer models that are supposed to predict that the Earth's going to heat up by 25 degrees in the next century. Well, fact of the matter is, those models don't work. They're completely worthless. There's not a single climate change model that works, unless you ignore, back up, unless you ignore these assumptions and you put in only the values and the data that you want. I've got a little cartoon on my door. You know who Michael Mann is? He's a scientist that is regretfully still employed by Penn State. He was the one that developed the infamous hockey stick model. Right? So here's the temperature. And here's the time, say maybe 1000 AD. Actually, even before that. It's like 1000 BC. And then here's today. He claims that the temperature over this time frame was very stable until the Industrial Revolution. And then it went like that. Okay? Looks nice. It supports his argument. Problem is, in his head, he was thinking that before he put that together. Okay? He wanted something that would justify his belief system. So what he did was, he went in here, and this is medieval time, right about in here. He ignored the medieval warm period, and he ignored the Little Ice Age. He just threw them out. Right? So I get a little cartoon that was written, I forget the author, for Dilbert, and they have this climatologist, his little cartoon figure, and he's made up to look like Michael Mann. And he explains, that we have, how do you do this stuff? How do scientists know this stuff? He says, well, we do. We have these models. We have all these models, and then we pick the ones that work, and we put in the data we want, and boom, there we go. And of course, when it came out in 2017, and when Michael Mann saw this little cartoon figure talking this nonsense, he knew it was a jab at him. So he got really bent out of shape. Anyway, models can be helpful. Models can be a political sledgehammer. Those are the climate models. So what happens when a model is wrong? If you're honest about it, it can teach you something about the real world. If your model's wrong, then you know that you're on the wrong track for that factor. So what do you do when the model stops working? Well, historically, sometimes we just restrict the application of the model. You can only use the model under these certain conditions, and anything outside that is invalid. Classical physics is a good example. All of Newton's formulas and models are only valid under certain conditions. When you get to extremely small or extremely large masses, then Newtonian physics falls apart. Right? So when it gets really small, we shift over to quantum physics. When it gets really big, we shift over to relativity and use different models. So that's one thing you can do, restrict its application. If possible, you may be able to modify the model, tweak it to make it respond to the new conditions. And then, of course, we can go to really ridiculous lengths. There are physicists who think that the world doesn't have 4 dimensions, height, width, depth, and time. So they've created models of the universe that have 26 dimensions. They have to be mathematical because there's no way you can represent them with a battleship. Sometimes what you have to do is just throw the model out and start over. You don't have any choice. So those are your 3 options. Good example. J.J. Thomson's plum pudding model of the atom. Right. When my mind's gone blank. When the gold foil experiment was performed and found that the atom was actually a very dense nucleus with electrons out here and mostly empty space, that model was thrown out in favor of a better one. Okay, so what do we mean by bond energy? The idea is that we can measure and predict how much energy it takes to break any one particular bond. And this process is going to be endothermic. So it'll carry a positive charge because the bond is the system, we're adding energy to it, that's positive. When bonds are formed, they go to a lower energy state, the components, and they give up energy, so those are exothermic, and that'll be a negative number. Now, how do we represent bonds? Well, there are a couple of ways. If we have 2 atoms, let's use hydrogen, because then we'll only have 1 electron. So if we do that, and they share electrons because they're not strong enough to pull electrons from each other, then 1 electron comes from that one, 1 electron comes from that one. That's a bond. And all bonds represented that way are 2 electrons. Okay, a covalent bond, I should say. So we also represent that bond this way. Okay. If we have oxygen, oxygen has 4 electrons between it, so it's a double bond. And nitrogen has 3, so that's 6 electrons in between. That's a triple bond. Now, what happens to the length of the bond? Well, as you increase the number of bonds between 2 atoms, you shrink the distance between them. It makes the stronger bond. Now, the difference is not linear. In other words, this is not twice as close as these 2. And this is not 3 times as close. And that's because of the nature of the bond. And I'll have to explain that to you later. But it is closer. It's just not a linear relationship. Let's see, this came out of my textbook, I think. So bond energies, so hydrogen bond energy is 432 here. HF is a greater bond energy. But HCl is less, HBr is less, HI is less. So that's hydrogen bonded with each of the halogens. Right? So we find that the bond energy is less as we go down, primarily because the halogen is a bigger atom and hydrogen can't get close enough to it. So the strength of the bond is less. But we can use these bond energies to predict the enthalpy of chemical reactions, right? So it's a two-step process, right? So if you have reactants on one side, for instance, let's take burning methane. So I'm going to draw it out with its bonds. There's methane. It has 4 bonds of carbon hydrogen. And then here's oxygen there. And it forms carbon dioxide and water. Okay? So, first thing we have to do is break all these bonds. Right? So we know what the bond energy of each one is. Back up. There we go. Carbon-hydrogen bond is here. So each one will take 413. Doesn't give me the units. I think is that kilojoules? Well, 413 units. So 4 times that to break this, and then double bond oxygen is 495 to break that one. That's how much energy you have to put in. And then when you form these bonds, you get that energy, get some energy back. 2 carbon oxygens, right? You get that much, 2 times that back. And oxygen hydrogen, you get that back twice. So if you take how much energy you put in, how much you get back, add those together, then the difference should be the delta H of that reaction. Okay. So we can do that like this. There's this formula. Say, here's the energy required, how much energy you put in, and then we subtract how much energy is released. This sigma, that's a capital sigma in Greek, means summation. So you add them together. All of the bond energies that go in, and then you subtract all of the bond energies and the reason we say negative here is because those bond energies, remember, they were all positive. Because they're measured in terms of how much energy does it take to break the bonds. So they're all positive numbers. So that's why this one has a negative sign on it. So here's an example. Predict the delta H for this one, given the following information. So we have 3 carbon hydrogens there, and 1 nitrogen triple bond carbon here. So we add 3 of these together with 1 of those, gives us a value. And then we say, all right, so we get these back, subtract 3 of these. So we put in for 3 of these, and we subtract for 3 of those. So those cancel out. They're neutral. So we really only have to focus on this one and this one. So we put in this much for that one, 891, and we subtract from that one. Oh, same thing. Wait a minute. Oh, I left out. There's a bond between this carbon and that nitrogen. And there's a bond between this carbon and that carbon. So actually, these cancel out too, and really we were only concerned with carbon-nitrogen minus carbon-carbon. So 305 minus 347 would be 42 kilojoules per mole, right? minus 42. Yeah, when you look at it that way, you can do it in your head. All right, now we're going to look at some models of bonding models. Right? The localized electron model, what does it mean? Well, it focuses on where the electrons are, and it says that the electrons are localized around specific atoms. So what does that mean in a practical sense? Well, we need some definitions. We need a foundation for the model first before we can use it. The electron pairs are assumed to be localized on a particular atom or in the space between it. So those are two possibilities. If it's in the space between, then those electron pairs are bonding electrons. Right? So they'll be the ones with the lines between them. But we may also have lone pairs, that is, those pairs that are not part of a bond. And they're assigned to individual atoms. And they will be written separately as two dots. Oops. Back up. Okay. So the localized electron model has several parts to it. And what we're going to do for this exam is focus on these two. And we'll get to this one for the next exam. But I just wanted to show you that they are all part of the same model. Part one is we have to describe where those electrons are. And we use Lewis structures invented by this fellow right here. And they center about the octets. We assume that octet is the ideal for each atom, and we put the electrons around the symbol for the atom, the ones that are available for that atom, for that element, and then we see how that interacts with other elements to satisfy the octet for each of them. Then we take that structure and we apply some other rules for predicting the geometry. And that's a submodel of this one, which is called the VSEPR. That just stands for valence shell electron pair repulsion. I'll show you what that means in a second. Lewis structures, or we have to know Lewis structures. We're going to start simple. So we draw Lewis structures for individual atoms. Right? So the Lewis structure for hydrogen is simple. It only has one electron. Right? So we draw it there. Remember, we've got 4 places around this symbol where we can put electrons. If we put 2 here, 2 there, 2 there, 2 there, then we would have a complete octet. But of course, hydrogen doesn't have room for it, right? Because it only has 1 s orbital. So that means 2 maximum, right? So hydrogen and helium are separate. They don't go by octets, they go by duets. So they have the duet rule, everybody else has the octet rule. So when 2 hydrogens, I should erase that. When 2 hydrogens come together, right, they've got those electrons out there. If they get close enough, then they do that. And the Lewis structure for that molecule is just that. We've accounted for all the electrons that were donated by the atoms are now part of the bond. And there are no lone pairs in this one. They're all bonded. How about fluorine?
Well, let's look at fluorine, the fluorine atom. How many valence electrons does it have? Right? So we go over here and say in this period, we go 1, 2, 3, 4, 5, 6, 7. It's 7 valence electrons. So we start putting them around. 1, 2, 3, 4, 5, 6, 7. And we have 1. We have 2, 3 paired and 1 unpaired. Now, if we're going to bond it with some other fluorine, we need to do this. This is a model after all, so we can change it to suit ourselves as long as we don't break any major rules. So there's fluorine. We have another fluorine oriented that way. There's the Lewis dot structure. We've accounted for all the valence electrons. Remember, the valence electrons are those that are available for bonding. The core electrons don't count. So when they come together, these two form the bonding pair. And the Lewis structure for that one is like this. Okay, with one bond between them. Okay, that's a single bond. If we were to write it like this, that means 2 electrons here, and then we could put the rest of them around like that. This is my preferred method. If they're bonding, I use a line. If they're lone pairs, then I draw the pairs. Okay, so let's talk about how to draw Lewis structures for compounds. For the compound, you sum up all the valence electrons of all the atoms. Then you arrange the atoms in the most probable arrangement, and sometimes that's tricky, but I'm not going to try to throw any tricks at you anyway. Unless you're told exactly how they go together, then you place the more electronegative atoms near the center, or the backbone of the molecule. And it's possible that you may have more than one valid Lewis structure. That happens. That's one of the Achilles heel of the Lewis model. Then you start placing your electrons in there. Start from the outside and work your way in. Right. So we need, water's too simple. Let's use something a little more complicated. How about Dinitrogen Pentoxide? About that one. Okay. How many total valence electrons are there? Nitrogen is 5 positions over, so each nitrogen has 5 electrons. So 2 times 5 is 10. And then oxygen has 6 each, so 5 times 6 is 30. So 30 and 10 is 40 electrons. So we have 40 electrons that have to be placed in this molecule. The nitrogens are going to be in the middle, I think. Let me change that. I would get in trouble doing that one. Dinitrogen Tetroxide. So now we have 10, and 4 times 6 is 24. So we have 34, right? Yep. Okay, 34 electrons. Now we have 2 nitrogens in the middle, and you just put a single bond to hold them together until you get the rest of them in there. And then the oxygens are going to be distributed like that. So there's, and each one of these is 2 electrons. So that's 2, 4, 6, 8, 10. So we've used up 10, and we have 24 left. So now you start from the outside and start placing your electrons. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Right? So they're all used up. We've got our electrons in there. Now what you have to do is establish the octets. Right? So this nitrogen has 2, 4, 6, doesn't have an octet. 2, 4, 6, right? 2 electrons here, 2 there, 2 there, that's only 6. Now these oxygens, they all have octets. Right? So how do we get octets out of this? Do we put a double bond here? In which case we'd have to steal 2 electrons from someplace. Or do we put double bonds here? Perhaps. So that's the dilemma in Lewis dot structures. Well, what we could do is simply take 2 electrons here and put them there, which will give us a double bond. And you still got 2, 4, 6, 8 on that oxygen, and 2, 4, 6, 8 on that nitrogen. If we do the same thing over here, then that's a possible structure. That's a valid Lewis dot structure. It may not be the only one, but it is valid. We could just as easily do it over here on that one and leave that one alone there, and leave that one alone. But be that as it may. Now, if we were to do oxygen, right, similar way, we produce this. Oxygen has 6. So 6 plus 2 is 8. So we need 8 electrons. 2, 4, 6, 8. We can't put any extra on hydrogen because it won't hold it. It only has duets. So this is actually the only Lewis dot structure. Now, once you get to this point, then we have to invoke the VSEPR model to say what's the geometry of the molecule. Okay. Well, here's another example. Right? So it can get pretty complicated. And I've got several examples for you to work out there that we can deal with next week. Well, all right. Let's see how we're doing on time. We got 1 hour left. How many more slides do I have? That's the $64,000 question. We'll get there. Okay. So I may have to come back to this slide. Let me look ahead a little bit. All right, these are exceptions. Exceptions to the octet rule. Why do we even have exceptions? Because the model says we need octets. But reality says you can't always have octet. Boron trihydride is one example. Right? If we say that is a real compound, so we have to deal with it. Boron has 3 electrons, and each hydrogen has 1, so that means 6 electrons to deal with. So we put boron in the middle, and each hydrogen, like that, 2, 4, 6, all used up. Boron doesn't have an octet, and there's no way to make an octet out of that. Right? Hydrogen doesn't have any extra electrons. So in this case, boron is deficient. It's less than an octet. But it's a real molecule. So you got to live with it. We can also go the other direction with these possibilities. And notice that we're, for sulfur and arsenic, with these halides, well, sulfur is in the third period, right? And it has extra electrons, has two that we couldn't find any place for, so they always go on the central atom. And sulfur can accommodate those extras because it's not going into a p orbital. Remember, this is n equals 3. So what do you have available at n equals 3? You've got a d orbital. Right? So those two electrons go into the d. Arsenic is down here. It's at 4. So it has available also d orbitals to form bonds with bromine. So that's how we rationalize the excess octet. Okay. Let's see. Let's take phosphorus pentachloride. Just do that one. So there's phosphorus. Okay. Then we take, what are the valence electrons for phosphorus? Would be 5. It's in the same family as nitrogen. So it's 5 electrons. And then chlorine has 7 each. So that's 35. So we have a total of 40 electrons that we have to place. Now in this case, phosphorus is not the more electronegative atom, but it will be in the center. Go figure. So we put the chlorines around it. So that's 2, 4, 6, 8, 10. We have 30 to go. So how many more can we hold here? 2, 4, 6. We can have 6 in each one of these. So that's 1, 2, 3, 4, 5 times 6 is 30. We use all of them up around the chlorine. And phosphorus exceeds the octet by 2. That is a real compound, so we have to live with it. You try for an octet if you can get it. If you can't, then you just live with it. Okay, let's see in this one. That's a review. Okay. So remember I said 3 things that you can do with a model when it doesn't fit the data. You can either restrict its use, you can tweak it, or you throw it out. So this is the second option. When you have more than one valid Lewis structure, then our tweak is to induce resonance. What do we mean by resonance? Well, this nitrogen trioxide ion, NO3-, which is one of our polyatomics, right? If we add hydrogen on there and dissolve it in water, you've got nitric acid. Right? So this nitrate ion, this is a valid Lewis structure. But if we shift that double bond around here and the electrons to make it fit, then we got another valid structure. We got another one over here. So you have 3 possibilities. So what do? Well, the localized electron model doesn't let you smear electrons. The electrons have to go someplace, and they have to be there as solid dots. Right?
So we make this one, and this one, and this one resonate with one another. So what that means is the reality is somewhere in the middle. Okay. That's resonance. They supposedly spend a little time here, a little time there, and a little time there. That's our tweak. The fact of the matter is, though, those electrons can move all over that molecule. We're going to get to that in chapter 9 with the molecular orbital model. Okay, let's see. We have time to do that. Now let's move on. Okay. Oxidation state. We talk about oxidation state. Yeah. So the oxidation state for an ion is the charge on the ion. And the oxidation state for an ionic compound is just the charge of the ions. The oxidation state on something like, let's see, I'm trying to think of something. Something with oxygen in it would be a good choice. So the oxidation state on NO2, nitrogen dioxide, we have to assume that some of the atoms are fixed. So we give the oxidation state for oxygen is just 2 minus. So that means we have 2 times 10 to the 4 minus. That means 4 plus for that nitrogen. Okay. That's oxidation state. But that's okay for things like electrochemistry. It helps you keep track of electrons. But if you're going to deal with covalently bound molecules in particular, you need another way of accounting for electrons. And so we came up with the formal charge. It's not really a charge. It just takes the form of a charge. Okay? So that's a useful distinction. It's not a charge, but it behaves like a charge. So how do we calculate the formal charge? Well, you need a Lewis structure first. And then if you have, let's say, let's use this one. I probably should do that. System here. There. And we have 2, 4, 6, 8. And then we have like that. What we're driving at here is when you have several valid Lewis dot structures, it's useful to be able to pick which one is most likely. The one that's most likely is the one that has the smallest summation of its formal charges. So the ideal situation is if we could come up with a formal charge for each one of these that was 0, that would be perfect. If we had to say -1, 0, and +1, then that would be acceptable. But if we had one that says -2, +3, something else, then that would be less likely. Okay, that's the whole purpose for our inventing formal charge, to try to pick the best Lewis structure. So how do you calculate formal charge on each of those atoms? The formal charge is the difference between the number of valence electrons that you would find on the free atom. Right, so that's where you start. Oxygen would have 6 valence electrons. 6, 6, 6. Nitrogen would have 5. That's where you start. Then you say, you use your dot structure to say how many electrons are actually assigned to that atom. Okay? All lone pairs belong to that atom. This is still the localized electron model. Right? So it's 2, 4, 6, and then bonds, you split them. So it's 2, 4, 6, plus 1 is 7. So it has 7 electrons assigned to it, where it started with 6. So that means its formal charge is -1. Okay. Same for this one, -1. Let's see, how about this one? So 1, 2, 3, 4, 5, 6, -6. That was 0 formal charge. Nitrogen, so 1, 2, 3, 4, it's +1. So +1, 0, -1, -1. Now let's see. I think we ignore that negative because we don't know where the negative goes. That's a negative charge for the whole thing. Oh, look at the formal charges. Add them up. -1, -2, +1 means -1. There's your -1. Okay, so the summation of the formal charges would be the same as the charge on the group. If it were neutral, then they should all add up to 0. But you want to minimize them as much as possible. And this is not bad. -1s, +1s, and 0s. That's good. Small good, big bad. Okay. So this is what it looks like in a formula, but I like doing it that way better. You know, pictures help me connect better than math. Sometimes math we have to use sometimes. Pictures are better for understanding. Okay. Let's see. Okay, that's what we did. So if we assign the formal charge for each one of these, like phosphorus starts at 5 because it's in the nitrogen family, the pnictogens. So 1, 2, 3, 4. 5 minus 4 is +1. So phosphorus is +1. Oxygen is 6 minus 7 because we have 6 and 7 here because that's half of that one. And 6 minus 7 minus 1. And then the chlorines are 7 minus 7. They're all zeros. Right? So if we add them together, this is a neutral compound. Oh, there it is. Okay. Have to add them all up, and they have to be equal to the charge on the group. If there's no charge, they have to be 0. Did you get this in high school too? Okay. You were privileged. I didn't get these until college. Later in college.
Yeah, we had all this stuff.
In fact, I wasn't introduced to formal charge until organic chemistry. Formal charge is really big in organic chemistry. Okay. Let's see. Okay, so this just says if you have more than one Lewis structure, then the one that minimizes or has more charges close to 0 is the preferred one. It would be the more stable one, as a matter of fact. So that's why this one is preferred over that one for carbon dioxide. They're both valid structures. Okay, so these are your precautionary notes. Like I said before, formal charge is not charge. Okay, it's just a way of bookkeeping, bookkeeping for your charges. And sometimes it's possible, even using formal charges, to get structures that really don't comport with reality. Okay, VSEPR model. Valence shell electron pair repulsion. This is key here, electron repulsion. The idea is that these valence electrons that are in the structure are trying to get as far away from each other as possible because they're all negatively charged. So they push, and we position them as far as we can get them away from each other. Lone pairs and bonding electrons alike. The name, though, is misleading because it's not always electron pairs. It's electron groups. We treat single bonds, double bonds, triple bonds equally. Okay, and I'll show you what I mean in just a minute. This is really jumping ahead. We'll come back to that. What we need is an example. You draw the Lewis structure. So let's say we have, let's take water. No, let's take carbon tetrachloride. So we know that carbon tetrachloride is this. Carbon is 4 electrons, and 4 times 7 for chlorine is 28. So that means we have 32. So we put carbon in the middle, all the chlorines around it. Oh, and I want to make this point too. When we talk about what's the geometry of a molecule, if there's only one central atom, then the geometry is just associated with that central atom. But if you have a more complicated molecule with several atoms strung out here with groups on it, then the geometry is for each of those central atoms. You know, one could be one geometry and the next one could be entirely different. Okay. But we're going to keep it simple at first. So there's 2, 4, 6, 8. So that's 24, right? No, 14. 24. Okay, so we can have 2, 4, 6 more around each one of these. 4 times 6 is 24. Okay. So we just need to do this, this, this. That's our dot structure for carbon tetrachloride. Now, what kind of structure will put these 1, 2, 3, 4? We focus on the central atom, and what does it have surrounding? Well, it only has bond pairs. So it has 1, 2, 3, 4 groups of single bonds. 4 single bonds around the central atom. The best, farthest away you can get those bonding electrons is the tetrahedron. So you put the carbon in the middle, and you put 1 chlorine up here, put 1 in the back, away, and then you put 1 out here and 1 out here. Right? So if you draw a connector between these, there's your triangular base, and then here's the other parts of the tetrahedron. You have to think 3-dimensionally. Okay, so that's the idea behind VSEPR. So what if you, let's see, the number of groups here. So if we have 2 groups, actually 1 group, and we have 2 groups around the central atom. We have 3 groups around, 4 groups around,
5, and 6. I stopped at 6. That's big enough. There's a difference between, if you have lone pairs in there, they're counted as individual groups. Right? So if you do have lone pairs, we have to distinguish between electronic geometry and molecular geometry. So we have electronic geometry is where you start. Then you go to molecular geometry by covering up the lone pairs and see what do you have left. So if you have one group, like carbon monoxide, right? If you only have one group there, it's always linear. That's the easy one. If you have two, like carbon dioxide, right, you have two groups, that's linear. And for this one, you don't have any lone pairs around that central atom. So it's also linear molecular structure. Okay. If you have water, for instance, well, water fits down here. Water would be you have to draw the Lewis dot structure, so that's what water would look like. So the electronic structure would be tetrahedron, right? Because you have 1, 2, 3, 4 groups. Like a tetrahedron electronic structure. And you cover these up, and what do you have left? You have a bent molecule. Your book might call it angular. I like bent better. Or like the first example, carbon tetrachloride, all of those groups are bonding pairs, so that tetrahedron would also be tetrahedral molecular. Okay? Or, here's another one. Let me move these out of the way. What if you have, well, if you don't have any lone pairs, this one will be trigonal planar. Same over here. But if trigonal planar has a lone pair in it, then it will also be bent. Now, if you have ammonia, is a good one. Okay, that's tetrahedral, electronic, but it's a trigonal pyramid. Right? Has a triangular base with a nitrogen at the top as a molecular structure. Okay. Let's see. So let's go down to 5. So what do you have with 5? Well, if you don't have any lone pairs, well, even if you do, the electronic structure for 5 is going to be Trigonal Bi-Pyramidal. So you would have a triangle down here with your central atom there. You have 3 around here, and then 1 up here, and then 1 down here. So you like 2 trigonal pyramids base to base. So that gives you positions for 5 at the greatest distance. Now, what happens if you have a lone pair? Where does the lone pair go? Right? It doesn't go up here or down here. Actually, the farthest away it can get from everybody is to put it on the triangle. And in that case, you get a molecule here, 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 and you get what you call a seesaw. If you have 2, now that's different. If you have 2 lone pairs, they go at the ends here. And then your molecular is trigonal planar. Okay? 6. If you have 6 and no lone pairs, well, even if you do, The electronic structure is octahedral. So what does octahedral look like? Well, it's like this pyramid, only now it has a square base. It's a square here, and then like that. And you have 8 sides. Then all you have to do is decide if you have one lone pair, where does it go? You know, I think I've got, let's see. Let me see if I got examples here. Do I? Here we go. These are examples where you don't have any lone pairs. Right? So we'll do the simpler ones first. Let's see. So there's your Trigonal Bi-Pyramidal. And notice the angles. So you can have different angles in there. Of course, with the, let's go back to this one. What's the angle here? This is the only one that you really need to memorize. The others you can figure out. 109.5. 109.5 angle right here. Okay? Now, if you have something like this, then the lone pairs, they're not constrained by bonding. Right? So they balloon out. When they balloon, they push everybody down. So that makes the angle smaller. So it might be 107 or something like that. Or if you like water, right, and you have 2 lone pairs, it pushes even harder on that vent, and the angle is even smaller. Okay, so for the Trigonal Pyramidal, remember on this triangle here, what's the angle? Well, you're going 360 around, so if you do it 3 times, you got to do it 120 degrees at a time to make 360. And the angle between this one and that one is obviously right angle, 90 degrees. So you have 2 degrees, 2 angles in the Trigonal Pyramidal, 120 and 90. In the octahedral, everybody's 90 degrees. That was easy. Let's see. So here we have 4 regular ones. So the molecular structure here is tetrahedral. If we've got a lone pair like ammonia, then you have trigonal pyramid. And if you have 2 lone pairs like water, you get bent. Okay? This one is your 5 pairs. So this one, if they're all occupied with bonds, then the molecular structure is the same. There's your seesaw. If you only have 1 pair, it sticks out here. Puts it as far away from the rest as possible. This one, I would have thought that it would put them up here, down here. But it says no. So if you have 2, okay, so I misspoke. If you have 2 lone pairs, they go on the triangle, and that's T-shaped. And if you have 3, they go on the triangle also. And that's, now your molecule is linear again. You probably already knew that, didn't you? Oh, you didn't remember that part? Okay. Okay. Let's see. Oh, predict the structure of each one of these. In order to do that, we need Lewis dot structures. Right. For this one, phosphorus pentachloride, we have a trigonal bipyramidal. For this one, we have a charged ion, and we've removed 1 chlorine. So now we've got 4 in there, which means it's tetrahedral. And for this one, we've added a chlorine, and that one makes it octahedral. So you can have those 4 different molecular structures
as products of this reaction. Now, are these polar molecules nonpolar? These are all nonpolar because the molecular structures are regular shapes. And any dipole moment that is experienced in these bonds they're all canceled out. Okay. For the longest time, the noble gases we thought would never form compounds. But chemists being the way they are, they have to force things. So they forced reactions on the noble gases, and it turns out that the xenon and krypton are the most likely candidates, and they do form compounds. It's just that they don't do it readily. Now, argon, neon, and helium, they've not been able to make compounds with them. They're too small. They're too happy where they are. In fact, argon is the Greek name for lazy. Okay, so we've established that xenon tetrachloride is a real compound. And if we draw the structure, we get 1, 2, 3, 4, 5, 6 groups, right? So 6 groups means octahedral electronic structure. And these two tend to go at the apex of the octahedron. So if we cover those up, we get a square planar. Right? So the molecule is going to be, let's see, does it show? Okay, this is a possibility. Here. This is a possibility that leads to that structure. So which one is right? You know, is it a seesaw or is it a square planar? So if it's in the first structure, the seesaw, the distance between the lone pairs is 90 degrees. But if we put them at the apex, they're 180 degrees apart. That's why I went for the square planar. I thought it would work better. And in this case, it does. That structure is preferred, square planar for xenon tetrachloride. Even though the bond is polar, the whole molecule is nonpolar. Oh, is that it? We finished off quick. Shocking. Okay, so try your hand at these review problems. So if they give me any trouble, next week we'll do a little review and then we'll go in the lab and do the Juman method. Real good. Half hour early. All right. Is there any pizza left? We'll have to try some. That's pretty good. Room temperature's not bad. You have a question? Yeah, okay. Which one is this? Molecular weight of mass. Okay. No, that's not it. For citric acid, I could look it up or I could derive it. Oh, let me shut this thing down. Stop.